Okay, so what we discussed yesterday, subsequences, right? And what we saw, if sequence is convergent, then it's every subsequence is convergent, correct?
Yes, sir.
And therefore, you can produce at least one subsequence which is divergent, then original sequence is divergent. Or if you can produce at least two subsequences, both are convergent, but they converge to different, then also original sequence is divergent. Right, because if sequence is convergent, every subsequence must converge to the same limit. Right, so that is what the important we discussed last time.
Sir,
Now, yes,
I have a doubt. If the subsequence, the limit of a subsequence is not x, then it is definitely certain that the limit of the sequence is divergent.
no, not necessary. If limit of a sequence xn is not x, then limit of xn is not x. That means x limit of xn may not exist or may exist, but it is not x. There are two possibilities. Am I right? For example, so see this. For example, if you look at sequence xn is equal to 2n plus 3 upon 5n plus 7. Okay, let us consider simple sequence. So consider sequence 1 upon n, and I will take subsequence I will take nk is equal to 1 upon 2k. Nk is equal to 2k. So if nk is equal to 2k, then what is the subsequence xnk? 1 upon 2k, right? Now, can I say that limit of xnk is not equal to 3? Can I say this?
Yes.
Right, because what is the limit of xnk? That is limit of 1 by 2k is 0. That we know in this case, but limit of xnk is not 3. This is also true. But from this, we cannot say that xn is divergent. Is it true?
Yes, sir. Okay, sir.
So this is not true, because xn may converge or may diverge, but limit of xn is not 3. That is sure. Because if limit of some subsequence is not 3, then limit of original sequence certainly not 3. But then limit is not 3 means there are two possibilities. Either it is divergent or limit exists, but it is different from 3. Right.
Yes, sir. Thank you, sir.
Okay. So you should think about all, because this statement has different versions, different interpretations you can have, and we saw some interpretations of this yesterday's theorem. What are the interpretations we discussed last time? So these are the different interpretations. So this was our statement, right? Then if xnk is a subsequence such that xn limit of xnk is not x, then either limit of xn is not x or limit does not exist. If sequence there is a subsequence which divergent, then original sequence is certainly divergent. If there are two subsequences having different limits, then original sequence is divergent. So now what is the importance of this? So before going further, let me tell you the we'll discuss the proof of monotone convergence theorem. So what is a monotone convergence theorem? What is monotone? What is statement of monotone convergence theorem? Do you remember?
If a sequence xn is monotonically increasing and it is bounded, it means that xn is convergent.
Right. If sequence xn is monotonic increasing and bounded above, So when we say monotonically increasing, means certainly it is bounded below without any uh, investigation, right? So if sequence xn is monotonically increasing and bounded above, then xn is convergent. Then xn is convergent, right? So when I say sequence is monotonically increasing, means x1 is less equal, x2 is less equal, x3 is less equal, and so on. Xn is less equal xn plus 1, and so on. Terms are increasing, so of course x1 is a lower bound, right? When I say sequence is monotonically increasing, first term is always a lower bound. So therefore monotonically increasing sequence is always bounded below, but if it is bounded above, then only convergent, otherwise not convergent. What is another statement? What is another statement? If a sequence xn is monotonically decreasing and bounded below, then convergent. Right, that means if sequence is monotonically decreasing x1, x2, x3, that means if you go to the higher terms, the terms are decreasing. But and if it is bounded below, there is something which bounds from lower side, then it is convergent. Right, this is what the monotone convergence theorem. So we'll discuss proof of this theorem because we left proof that time. So and then we'll use this theorem to prove something about to discuss something about subsequences, right? So we'll prove only one of this, and then second is similar. So we'll prove first. Suppose xn is monotonically decreasing, monotonically increasing, right? Suppose xn is monotonically increasing. Therefore, by definition of monotonically increasing sequence, xn is less than or equal to xn plus 1 for all n, correct? Now, what is our assumption? Assume that xn is bounded above. Right, because our assumption in the statement is, what is our assumption? If sequence xn is monotonically increasing and bounded above, then xn is convergent. So what is our claim now? What is claim?
Xn is convergent.
Right, so xn is convergent. So this is our claim. Fine. But to prove that xn is convergent, that means we have to identify a number and we have to show that, okay, this number is a limit for this sequence. So we have to investigate a number, and that number is a limit, and we have to prove that, okay, see, this is a limit of this sequence, that we should want to prove, right? Okay, the what is the right candidate which could be a limit of this sequence? What will be a right candidate? Key, and we'll investigate. We have to search that number which is a limit of this sequence, and we'll show that, see, this is a limit. Yes, logically, do you understand what we want to do?
The lowest upper bound.
Yes, because our tendency x1, x2, x3, the tendency of sequence is increasing. And we are also assuming that it is bounded above, right? So consider a set A, which is xn. Now consider a set A. Then A is called as the range of sequence xn. Range of sequence xn. Now, do you understand what is the difference between sequence xn and set A, which contains terms of sequence? Do you understand the difference, or they are same? What is your guess? They are same or they are different?
They are different.
They are different. Okay, let us see example. Right, so you have everything should be clear. Suppose I take a sequence xn is minus 1 raised to n. Look at this sequence. Okay, now what are the terms of this sequence? Minus 1, 1, minus 1, 1, minus 1. How many terms this sequence has? How many terms?
Infinite.
Infinite.
Very good, infinitely, because these terms have a specific position. So first term is minus 1, second term is 1, and so on. But for this sequence, if I am going to construct the set or range set, right? Then what is my set A in this case? Set means it is a set, and in set we do not repeat the elements, right? Sequence is a different thing and set is a different thing. So what are the accents or what are the numbers? What are the numbers which
Minus
ah,
1
1
and 1.
times 1.
One.
right? And therefore this set has only two elements, and sequence has infinitely many terms. So the difference is clear. What is the difference between the terms of sequence and set, which is a range of sequence? Is it clear?
Yes, sir.
Right. So now I am considering terms as a numbers. So since xn is bounded above, there exists number m such that xn is less than or equal to m for all n. Here I am not saying m is positive. Why? M may be negative because just it is just upper bound. For example, see, you should think about worst to the worst possible situation. For example, look at sequence xn is equal to minus 2 minus 1 by n. Right. This sequence, if you see, first term is so minus 2 is here. First term is minus 1 minus, right, minus 2 minus 1 by 1. Second term is minus 2 minus 1 by 2, and so on. So this is increasing sequence. Is it clear? And xn are less equal minus 2 or xn are less equal minus 1 for all n. So therefore minus 2 or minus 1 or minus 1.5 are upper bounds. Correct? So not necessarily upper bound is positive. I am not saying that my sequence is positive numbers or negative sequence. It is any sequence, but it is bounded above, monotonically increasing. So xn is bounded above. So therefore each term is less equal some m for all n. Correct?
Yes, sir.
Yes. Therefore, can I say that set A is bounded above?
Yes, sir.
And A is non-empty? Am I right? Therefore, A is a non-empty subset of R which is bounded above. Right, so look at this sequence. Xn is equal to minus 1 raised to n, and my set is in this case minus 1 and 1. Xn is not monotonically increasing this minus 1, but what is set A? Range. Fine. So this set is bounded above and it is non-empty subset of R. So what we can see? What we can see? Which property we can apply now? By which property? Okay, so what is the completeness property of R? What is completeness property of real numbers? What is completeness property of real numbers? Yes.
The
Will you able to-
supremum of A would be belongs to R.
Right. If set is bounded above, then it has a supremum in real numbers. If set is bounded below, every non-empty subset of R which is bounded above has supremum. Right. Upper bounds are, there are many upper bounds, but supremum is least upper bound. So if set is bounded above and non-empty, then certainly set has supremum. If set is bounded below and non-empty, then it has infimum. So this set is non-empty because the terms of sequence, at least some number is there. So it is non-empty, bounded above, it has a supremum. So A has a supremum in R. So let alpha is equal to supremum of A. Right? Supremum is least upper bound. Now what is our claim?
Limit of xn is alpha.
Right, because we were searching for the right candidate which could be a possible limit of xn, and now we found something, some number is there which is supremum of set A. So we claim that limit of xn is alpha. Now our job becomes easy because we found some candidate which we can prove, which we can expect. We hope that this is a limit for sequence xn. If we are able to prove, then we are done. Right. Okay, so how to prove? How to prove? That is
Epsilon.
given epsilon, we can produce k such that xn minus alpha is less than epsilon for all n greater equal k. So this is our aim, right? This is our claim. And so how to start the process? Once our claim is clear, how to yes, how to initiate the process?
We take an arbitrary epsilon.
So given epsilon, somebody gives you epsilon because your claim is, or your uh, you are claiming that the limit is alpha, and therefore somebody gives you epsilon and you will produce k, then you are done. So given epsilon, want k. This is what in my mind, what I want. So given epsilon, now I want k. Okay, so but we'll use the properties of supremum and all these things. Right. Okay, let us use properties of supremum. What properties we can use of supremum? So our sequence is increasing. That is our interesting fact given. So terms are increasing, x1, x2. So terms are in increasing order. And alpha is somewhere here, which is a supremum of all these terms. Right. Now what can you say about alpha minus epsilon? What can you say about alpha minus epsilon? Since alpha is the least upper bound, A, alpha minus epsilon is not an upper bound of A. Am I right?
Yes,
Yes.
sir.
Yes, sir.
Right. So alpha is least upper bound. So alpha, if you subtract epsilon, it cannot be upper bound. What does it mean?
There exists xn belonging to
Ah,
A such that
there exists k, suffix k, such that the corresponding term is greater than, right? So corresponding term is here. There are many, but there is some key. The corresponding term is greater than. Okay, let me write in some different way. So the corresponding term xk is greater than alpha minus epsilon, such that alpha minus epsilon is less than xk is less than or equal to alpha. Am I right? Right. So,
Yes, sir.
right, because alpha minus epsilon is not an upper bound of A, and A contains the terms of sequence. Right. A contains terms of sequence. Right. And therefore, some xn is certainly greater than alpha minus epsilon. Let us that xn is x suffix k, and choose that particular k. That could be x100. The x100 is, right. K could be 100. Then x100 is greater than alpha minus epsilon. But certainly some number is there, some term is there. Right. Now, what is the tendency of sequence? Since what is the tendency? Increasing. Since xn is increasing, right? Since tendency of sequence is increasing, tendency of sequence is increasing means what? Suppose my sequence xn is increasing, what is the relation between x5 and x3? Which is greater if my sequence is increasing?
X5 is greater.
X5, right? Because if my suffix is larger, right, then the corresponding term is larger. That is why, what is the meaning of increasing? So x1, x2, x3, x4. So tendency of sequence is increasing. Therefore, my suffix is larger, the term is larger. Similarly, so since xn is increasing for n greater than or equal to k, what is the relation between xn and xk?
N is greater than xk.
Ah, greater than. And xk is already greater than alpha minus epsilon. Xk, this is a particular term which is greater than alpha minus epsilon. So xn is greater equal xk and alpha minus epsilon, correct? Because tendency is increasing. Therefore, what? If,
Xn is greater than alpha minus epsilon.
right, so therefore if n is greater equal k, then alpha minus epsilon is less than xk, xk is less than or equal to xn, and all terms are bounded above by alpha supremum, right? All terms are bounded above by alpha, which is a supremum, and this is less than or equal to alpha plus epsilon. Here, what I have written last expression, is it clear?
Yes,
Yes,
sir.
sir.
Right. Therefore, ultimately what we found, alpha minus epsilon is less than, xn is less than alpha plus epsilon for each n greater equal this particular k. What is that k? The suffix of the term xk, which is greater than alpha minus epsilon. We have selected one, we select one term and look at its suffix, call it as k, and then we are looking at n greater equal that k, right? So can I say that E minus epsilon less than xn minus alpha less than epsilon for all n greater equal k, right? Is it same as xn minus alpha is less than epsilon for all n greater equal k, right? What is the conclusion?
Alpha
Hence,
is limit of
right?
xn.
And we select arbitrary epsilon, and for that we could find k in general. So epsilon was just arbitrary. So hence, for any, we can produce k, right? Whatever epsilon, we are always able to produce k such that xn minus alpha is less than epsilon for all n greater equal k. Therefore, limit of xn is alpha. Right, so this is what monotone convergence theorem which we already used, but proof is this. And see, sometimes you should have some common sense. Ki tendency of sequence is increasing, and if something is upper bound or bounded up, and therefore somebody stops, somebody is there, will stop the increasing sequence. That means what would be the tendency of sequence is increasing. That means it will not go down. So tendency is throughout increasing. Therefore, where it will settle, right? Where it will settle. Suppose you launch a rocket and it is just going up, and some obstacle is there where it will collapse, right? The point where, which is the lowest point where there is obstacle, right? So, and therefore infimum, supremum is the point where it will settle, correct? It will not settle at higher position, or it will not settle at some higher position. So it will settle only at least upper bound, not at any other upper bound. So supremum, right? Now, if this statement is proof is clear, then what this proof has to do with subsequences? So there is one more very interesting theorem. That theorem is monotone subsequence theorem. So what monotone subsequence theorem says, every sequence has a monotone subsequence. Every sequence has a monotone subsequence. Is the statement clear?
Yes, sir.
Right. So what statement says, you choose any sequence, then you can always extract a subsequence from that sequence which is a monotonic increasing even or monotonic decreasing, even your sequence xn is not monotone. For example, look at sequence minus 1 raised to n. Is it monotone sequence?
No.
Right.
Yes, yes. No, sorry.
So is xn monotone? No.
No.
Right. It is not monotone because some terms are in -1 and some terms are 1, going in one direction. So terms are just oscillating like this. But can we extract a subsequence which is monotonic?
Yes, sir.
Yes, sir.
Can you produce a subsequence xnk of xn which is monotone? And answer is certainly yes, because if you look at xn, if you look at nk is equal to 2k, then xn, what is it? 1, which is monotonic, increasing as well as decreasing, right? This is a monotone subsequence. Original sequence is not monotone, but we can extract a subsequence which is monotone. We can extract one more. right? You can extract one more. Nk is equal to 2k minus 1. Then what is xnk?
-1.
Minus 1. And this is also monotone. Can you extract a subsequence which is not monotone? Can you extract a subsequence which is not monotone? Yes. Can you extract a subsequence which is not monotone?
Yes, sir.
For example, 3k.
Nk is equal to 3k.
Right. Then what is xnk? Yes, minus 1 raised to 3k. And what are the terms? Some terms are plus 1, some terms are minus 1. Right. For example, if k is equal to 1, what is the first term? Minus 1. K is equal to 2, 1. Minus k is equal to 3, minus 1, and so on. So, this is not monotone. So, what is the moral of the story? Given any sequence, you can always extract a subsequence which is monotone, or you can also extract a subsequence which is not monotone. Anything is possible. But certainly, this monotone subsequence theorem says that every sequence has a monotone subsequence. Right? From every subsequence, always extract monotone. So, okay, so statement is clear.
Yes, sir.
Okay, so we'll discuss proof of this theorem later on, because right now proof is not very important. The only thing is the statement is important. It is possible to extract a subsequence which is monotone. Now, question I would like to ask: if xn is a bounded sequence and xnk is its subsequence, then is xnk bounded?
Yes, sir.
Of course, right?
Yes.
Because all terms are bounded, all terms of sequence are bounded, and xnk are some terms, some of them. Certainly they are also bounded. Correct?
म्हणजे थोडं कानात हे होईल. कान पडी.
Is it clear?
Yes,
Keep
sir.
your mic off. Mayur. Mayur, keep your mic off. Right? So xnk are the some terms of xn, right? Some terms are deleted and some terms are in xnk. So if original xn all terms are bounded by some number, then right, certainly xnk is bounded. So answer is certainly yes, without any difficulty, right? It is very straightforward to see this. So now, okay, this previous sentence is clear. What I said,
Yes, sir.
Yes, sir.
xn is bounded, every subsequence is certainly bounded, no doubt. So Bolzano-Weierstrass theorem. This is also very important theorem in analysis. Very important theorem, Bolzano-Weierstrass theorem. Every bounded Okay, before this, I would like to ask one more question. If xn is a sequence, can you produce a subsequence of xn which is convergent? You understand? If xn is a sequence, then can you produce a subsequence which is convergent? Can you extract a subsequence which is a convergent? Can you extract a subsequence which is convergent?
Yes, sir.
So, okay, for example, look at a sequence xn minus 1 restraint. Not convergent, but we can produce subsequence xnk, that means x2k, right? This is convergent. Am I right? Yes. Is it clear? Question is clear. If xn is a sequence, can you produce a subsequence? Now, but what is the answer? Answer to this question, yes or no? That is the point.
Sir, answer is yes.
Okay, so okay, I gave you example minus 1 restraint. In that case, I can produce, but I will give you another sequence 2n square, for example. Right? Can you produce a subsequence which is convergent?
No, sir.
No, sir.
Right? In this case, no. And therefore, in general, answer is no. Can you produce a subsequence xnk of xn which is convergent? Right? And in this case, answer is no. Now, what is the difference between these two examples, 1 and 2?
First sequence is bounded, and
Right.
second one is
Right. So this is a key point, and therefore, what is the Bolzano-Weierstrass theorem? Every bounded sequence of real numbers has a convergent subsequence. If sequence is bounded, then certainly it has a convergent subsequence, no doubt. But if sequence is unbounded, there is no guarantee. Right? If sequence is unbounded, there is no guarantee. If sequence is unbounded, then can we say that you cannot produce a convergent subsequence?
No.
No, because if C1 sequence is unbounded, you can have convergent subsequence. You may have, may not have. Right. So, statement is clear. Every bounded sequence of real numbers has a convergent subsequence. Okay. So, suppose xn is a bounded sequence of real numbers. Okay, now what is a monotone subsequence theorem? Monotone subsequence theorem says that every sequence has a monotone subsequence. Every sequence has a monotone subsequence. That means you can extract a subsequence which is increasing or decreasing. right? So therefore, no matter your sequence is bounded or convergent or whatever, you can always produce a monotone subsequence. So by monotone subsequence theorem, there is a subsequence xnk of xn such as xnk is monotone, right? Xnk is monotone means what? That is xnk is either increasing or decreasing monotonically or decreasing, right? So there is a subsequence which is either increasing or decreasing. Either increasing or decreasing means what? So xnk is increasing means what? Xnk is increasing means what? The term at higher position is larger. Means what? Xnk and xnk is less than or equal to what?
X and K plus 1.
So because next position is k plus 1 position, right? Xnk is decreasing means what?
X and K is greater
Xnk,
than X and K plus 1.
right? So xn is bounded, that is our main assumption, but by monotone subsequence theorem, every sequence has a monotone subsequence, so we can extract a subsequence, we can delete some terms so that whatever remaining is a monotonically increasing or decreasing. So we have selected or we have extracted a subsequence, right? We have extracted a subsequence xnk which is monotonic. Original sequence is bounded. Since xn is bounded, we have, is xnk bounded?
Yes, sir.
Xnk is also bounded. So what is the effect of this? Therefore,
X and K is convergent.
right, xnk is a monotonic as well as bounded. And bounded. And therefore, by which theorem?
Monotone convergence theorem.
Monotone convergence.
Therefore, by monotone convergence theorem. So by monotone convergence theorem, xnk is convergent. Right, and therefore we used two theorems, monotone theorem and monotone convergence theorem, the Bolzmann-Weierstrass theorem. So by monotone subsequence theorem, it has a monotone subsequence, and since sequence is bounded, that the subsequence is also bounded and therefore convergent. And what is our conclusion? Thus, every bounded sequence has a convergent subsequence. Right, so every bounded sequence possesses a convergent subsequence. Right. So uh, if xn is if sequence xn is monotonic, increasing, if sequence xn is monotonically increasing, okay, before this, I would like to ask one question. Is suppose xn is a sequence, suppose xn is a sequence, any sequence, just a sequence, not increasing, decreasing, nothing. If xnk is a subsequence of xn such that xnk is convergent and limit of xnk is alpha, then can we say that xn is convergent?
No, sir.
No,
No,
right?
sir.
If some subsequence converges, doesn't mean that sequence is convergent, right? Doesn't mean that sequence is convergent. Okay. One and second question I would like to ask, if xnk and xnr are two subsequences of xn such their limit that limit as k tends to infinity xnk is same as limit as r tends to infinity xnr is alpha. Can we say that xn is convergent?
No, sir.
Right. Right. So here answer is no. Here also answer is no. That means if one subsequence convergent doesn't mean that sequence is convergent. Or if two subsequences are there and converging to same limit doesn't mean that the sequence converges, because there are many other sequences which may converge to some different numbers, and therefore by subsequence criteria sequence may not converge. Right. So is it clear? Answer is no in both of the cases.
Yes,
Correct?
sir.
But
Yes, sir.
Yes, sir.
now, but there is some interesting thing. If xn is monotone, increasing, suppose xn is a monotonically increasing sequence. If xnk is a subsequence of xn such that limit as k tends to infinity of xnk is alpha, then limit of xn is also alpha. This is very interesting thing. Just compare the first question and this example. The first question. Xn is a sequence and xnk is one of its subsequence which converges. You cannot say xn is convergent, right? But here, what is the difference? Read this carefully. What is the difference?
Xn is
monotonic.
monotonic increasing.
Right. If xn is a monotonically increasing, then one subsequence is sufficient to guess the limit of sequence. Am I right? Is it clear? One
Yes, sir.
subsequence is one subsequence gives the information about the sequence. But in general, this is not true. But if sequence is monotonically increasing, then that is true. Right. And how will you prove this? So suppose xn is monotonically increasing. Suppose xn is monotonically increasing. Therefore, xn is less than or equal to xn plus 1 for all n. Now, if suppose xnk is a subsequence of xn with limit of xnk is alpha convergent and its limit is alpha. So what is our claim? What is our claim?
Limit of xn is also alpha.
Right. So we claim that the limit as n tends to infinity xn is also same number alpha. And how interesting is this? Because can you see tendency of sequence is increasing, right? X1, X2, X3, X4 and so on. Now I am looking at some subsequence. So I am deleting some terms. For example, I am deleting some terms, right? Then what happens? If I delete some terms, then some terms remains, but the tendency of subsequence is also increasing, right? So tendency of subsequence is also increasing, correct?
Yes, sir.
Now what is going to happen actually if the subsequence goes to alpha, then what about the in between terms? What about the in between terms? Do you see the, can you see the proof actually? This is alpha and okay, let me draw some figure here. This is my original sequence and okay, and what is my subsequence? These are my terms of subsequence. These are blue are terms of subsequence, red are all the terms, remaining terms. And since we are assuming that x and k converges to alpha, that means given any epsilon, I can find k such that all terms are in this distance, alpha minus epsilon to alpha plus epsilon. What about the in between terms which are not in the subsequence? Are they in the same neighborhood?
Yes, sir. They are in the same neighborhood.
Right, and because the tendency of sequence is increasing, it will not happen that some terms will go away, become smaller and or becomes larger. So the tendency is increasing. So all in between terms which are not included in subsequence, they are also in same neighborhood, and therefore all terms after some k are in this neighborhood. Do we see the proof actually from this figure?
Yes, sir.
Right, and then from that you can decide your strategy how to prove. Right, you think about it. Next time we'll see the discuss the proof, but this is a strategy. First of all, try to see the proof, try to imagine the proof, and then write down the proof. That should be the strategy, right? Okay, so any doubt?
No,
No,
sir.
sir.